Hello everyone, this is Rui PCB, your trusted PCB partner. Today our topic is multiple strategies for 6-layer board microvias. Which one is best for your design? Welcome back to the 6-layer board microvia strategy course. In the previous video, we understood the advantages of 6-layer boards as well as their core concept of providing more signal and rational layers. Today we will dive deeper into the specific connection strategies for 6-layer boards. Different connection methods require different stackups, and these will affect the electrical performance of the PCB. Let's take a look together at which stackup is best suited for our design. Let's first take a look at the 6-layer standard stackup. This is a relatively common connection method. Signal, ground, signal, power, ground, and then signal. This is the most commonly used and recommended 6-layer stackup. It's the most classic, widely used, and optimal in terms of performance among 6-layer boards. What other advantages does it have? The first is excellent signal integrity. We can see that layers 1, 3, and 6 are all signal layers, and each is paired with a dedicated reference plane. L1 references the GND on L2, L3 references the power on L4, and L6 references the GND on L5. Each signal layer has its own independent reference plane, which allows for excellent impedance control and low impedance return paths for all signal layers, greatly reducing signal reflection and crosstalk. Second, it provides outstanding power integrity. The close coupling of the L5 ground plane and the L4 power plane forms a large area, low impedance plane capacitance, providing a very stable power distribution network and effectively suppressing power noise artifacts. Third, powerful EMI and EMC performance. The L2 and L5 layers of the CND start up excellent electromagnetic shielding, with the internal signal layer being sandwiched between the power and ground screens, further reducing external radiation and mutual interference. The L3 signal layer, which is in the middle, is completely shielded. Fourth, flexible and unlimited capability. 3 high-performance signal layers are activated, which can be allocated according to signal type to improve mutual efficiency. The drawback is that the cost is relatively high. The more PCB layers there are, the higher the cost requirements and the more complex the design becomes. Suitable scenarios include almost all electronic products that require high performance, high density, high speed, excellent signal quality, and complex mixed signals, as well as those with EMI, EMS requirements, such as PC motherboards, wireless devices, high performance communication networks, high-end industrial controllers, and so on. Are there any other common 6-layer stack-up methods? Yes, there are. Let's take a look at them as well. I've also listed 2 other types here, each with its own pros and cons. Although the solution we just discussed is the most recommended, there are other recommended methods suitable for specific scenarios. For example, in Scheme B, signal, ground, power, ground, signal, power. This recommended method may provide 2 power planes or place the reference planes closer to the center, but it could result in some signal layers not being able to access the reference row, or the power and ground plane arrangement not being as balanced as the methods we discussed today. The third scheme is signal, ground, signal, ground, signal, power. With this approach, if more signal layers are needed and the requirements for power integrity are lower, it may be possible to place 2 signal layers together. However, this will increase crosstalk between these 2 signal layers. These are all choices made under specific circumstances, but generally we recommend the more standard approach. How do we assign dedicated signal layers for different types of signals? A six-layer board provides multiple signal layers, allowing us to intelligently allocate them based on signal characteristics, further optimizing the design. L1, which is the top signal layer, is best suited for placing critical components such as BGA chips and the most sensitive highest speed signals like memory interfaces and clocks, because directly beneath it is a solid pure plane that provides optimal impedance control and return path. L2 is the GND layer, serving as a complete reference ground plane, providing return paths for L1 signals and serving as a reference for L3 signals. Since it connects two signal layers, this structure ensures its integrity. The L3 signal layer is suitable for placing secondary high-speed digital signals or signals that are routed orthogonally to those on L1 in order to reduce crosstalk between layers. Its reference plane is the PWR layer below. The reference plane for L3 is L4, not L2. L4 is the power layer. Layer 4 is closely coupled with Layer 5, which is a low power, low speed power supply, and these two form a tightly coupled power pair. Layer 5's GND serves as the reference for the bottom signal layer and can also be used as a heat dissipation material for a small number of low speed components. Layer 6 is the bottom signal layer, suitable for placing medium and low speed digital signals, analog signals, or control signals, and it references Layer 5. Today, we have thoroughly analyzed the most commonly used and recommended stack-up configuration for six-layer boards. We have understood its main performance in terms of signal power, EMI, and the overall system. We also learned how to assign each signal layer in a six-layer board based on signal type, which is a fundamental skill for firmware tasks. Mastering these six-layer board stack-up strategies is even a key capability when designing high-performance, highly complex PCIe 10 systems. I hope this content has inspired you and wish you success in becoming an outstanding electronics engineer. If you enjoyed this video, please subscribe to my channel for more content. Thank you all.